Lesson 7 is key features from rules of quadratics, and rules are just basically the way that we write the function. So quadratic rules can come in three different forms. They can be in standard form, factored form, or vertex form. 7.1, we're going to start off with standard form. So standard form is f of x equals ax squared plus bx plus c. A, b, and c must be real numbers, meaning they can't really involve I. And then a cannot be 0, because if a is 0, then that cancels out this entire x squared term, which x squared has to be there in order for it to be a quadratic. First, we're going to break down what it means if we have different a values. So a is the lead coefficient. Whether it's positive or negative tells you if the graph is increasing or decreasing, and the direction that it opens up or down, basically. So if you have a positive a value, that means that the graph is going to open up. So it could be anywhere on the coordinate plane, but it's going to open upward no matter what, if it has a positive a value. And then that also tells us what the end behavior is. So remember, end behavior is just basically where is the left side of the graph finishing and where is the right side of the graph finishing. So the first line, as x, this arrow means approaches. So this is read as x approaches negative infinity. That just basically means as the graph goes left. Because x approaching negative infinity means the x values are getting smaller, and that happens on the left side of the graph. And then this is f of x approaches, so it's asking, is it going up or is it going down? So the left side of our graph finishes going upward, so f of x is approaching positive infinity. And then the second line, this is as x approaches infinity. So that means the x values are getting bigger. That happens on the right side of the graph. So as the graph goes to the right, f of x approaches, is it finishing up or is it finishing going down? So the right side of our graph finishes going upward, so this would also be positive infinity. So if it finishes going up, it goes, f of x goes to positive infinity. If it finishes going down, f of x would go to negative infinity, and then you would write that whole thing each time for end behavior. You wouldn't just put the two infinities at the end, you would write the whole kind of sentence statement thing. Okay, so when we have a negative a value though, when the lead coefficient is negative, the graph opens down. So it can go anywhere on the coordinate plane, it just has to be opening down. And then for end behavior, this is as x approaches negative infinity, so that's the left side of the graph. The left side of our graph finishes going downward, so f of x approaches negative infinity. Remember, f of x is just y, like the y coordinate, so if the graph is going down, the y values are getting smaller as it goes down, so that's why f of x is approaching negative infinity. And then as x approaches infinity, so the right side of the graph, f of x approaches, the right side of our little graph finishes going downward. So f of x approaches negative infinity as well. And that's the case for any graph that has any quadratic that has a negative a value. Both sides are going to finish going down. So these sketches help us find the end behavior for any quadratic that falls under that category of positive a value or negative a value, and they'll all fall into one or the other. And then for finding the y-intercept, there is a shortcut. I'm going to show you the long way first, and then you can use the shortcut after. So I'm going to draw a little sketch off to the side here. So if I have any graph, but I'm going to make it a quadratic graph, and there's a y-intercept, any point that is a y-intercept has an x-coordinate of 0, and then we'll say the y-coordinate is just y. That'll be whatever number it crosses at. But every single y-intercept has an x-coordinate of 0. That's what makes it on the y-axis, is because we're not going left or right at all for the x-coordinate. So in order to find the y-intercept, that just means that you have to take a 0 and you have to plug it in for x, because every y-intercept has an x-coordinate of 0. So we say we find f of 0. That means that 0 is going in for x. It'd be equal to 0 squared plus 4 times 0 minus 5. And then 0 squared, 0, so that goes away. 4 times 0 is also 0, so that goes away. And then I'm just left with that negative 5. So our y-intercept is negative 5, and you'll notice that that was the constant term c from the original problem, and that is always the case when it's in standard form. So the c value, the constant term, the number without the variable, will always tell you your y-intercept when it's in standard form, because if I were to plug in 0 for my x's to find the y-intercept, this would cancel out, and this would cancel out. So I would just be left with C. So the next form that rules can come in is called factored form, and you may also see this called intercept form. So the formula is f of x equals a times x minus r1 times x minus r2, where r1 and r2 are the roots or the zeros, or I'm also going to add x-intercepts. So factored form can come from factoring standard form, so that's what we're going to do. So over here, find the x-intercepts of f of x equals x squared plus 4x minus 5. So since a is 1, the lead coefficient is 1, I just need, in order to factor it, I just need numbers that multiply to c and add up to b. So multiply to -5 and add up to 4. So I can use 5 and -1. So this would be f of x equals, it'll be x plus 5 times x minus 1, or I could write it as like x minus 1 times x plus 5, the order doesn't matter. And then to find the x-intercepts, so another like word for x-intercepts is zeros. And we've talked about finding the zeros of the function before. That means that we take 0 and we like replace the entire f of x with it. It's what x value is going to make the function equal 0. So we have to replace f of x with 0. So it'd be 0 equals x plus 5 times x minus 1. And then from there, it's in factored form already. So now we just need to set each factor equal to 0. So we'll do x plus 5 equals 0. And then x minus 1 equals 0. And then we'll just solve each separately to get x by itself. So if I subtract the 5 over, I would get x equals -5. If I add the 1 over, I would get x equals 1. So those, like, yes, we just solved, but like solutions and x-intercepts, like they're all the same thing. They're all in the same family. So this is an x, these are both x-intercepts. So x equals 5 or -5 and x equals 1. So the next example, find the end behavior. This is a typo. It should say y-intercept right here. But find the end behavior, y-intercept, and x-intercept of the function f of x equals -2x squared minus 7x plus 1. So I'm going to separate these into parts. So I'll say part A is end behavior, part B is y-intercept, part C is the x-intercepts. So for A, for the end behavior, we're really just looking for one thing. We're looking for if the A value is positive or negative. So our A value is -2. So it's negative. So we have a negative A. And that tells us all we need to know for end behavior. If it's a negative A, the graph is opening downward. So we would write our end behavior as x approaches -infinity. So that's the left side of the graph. You can see from our little sketch, like the left side of the graph goes down. And that's always, whenever there's a negative A, both sides are going to go down. So as x approaches -infinity, f of x approaches -infinity also because it's going downward. And then the second line, as x approaches infinity, that's the right side of the graph. So the right side of my graph is also going down because both sides are going down. So f of x approaches -infinity there as well. And if you ever have a problem where, so specifically for quadratics should always finish going in the same direction. So both positives or both negative infinities. It's not the case for every function, but quadratics should always finish going in the same direction. And then for part B, our y-intercept. Remember with when it's in standard form, our y-intercept is just our constant term. So in this case, it's 1. So that number, like, we don't really have to do any work to find it. It's just like, you know, if we're going to plug in 0 for x, like this term would go away and this term would go away, and we'd just be left with that constant 1. So our y-intercept is 1. If it wasn't in standard form, we would have to do some work. We would have to find like f of 0 where we plug in 0 for x. And then part C, so X-intercepts. So I'm gonna rewrite this really quick. So f of x equals negative 2x squared minus 7x plus 1. Okay, so a is not 1, so that doesn't necessarily mean it's not factorable, but we definitely need to like check a little bit harder to see if it's factorable. So we would take a times c, so it's 2, negative 2 times 1, which is negative 2. And then b is negative 7. So in order for it to be factorable, we would need numbers that multiply to negative 2 and add up to negative 7. So those numbers don't exist, so that just means it's not factorable. So if it's not factorable, then, I mean, there still could be x-intercepts, but you have to find them a different way. You have to use a different method of solving quadratics. So it's not factorable, you can use completing the square or the quadratic formula. This would not be a good one to use completing the square because I would have to like divide everything by the lead coefficient negative 2, which is going to give me like something funky to work with. So I'm just going to use the quadratic formula. So my a, b, and c, a is negative 2, b is negative 7, c is 1. So if I use quadratic formula, it would be x equals negative b, so that's negative 7, plus or minus the square root of b squared, so negative 7 squared minus 4 times negative 2 times c, so times 1, and then all over 2a, so 2 times negative 2. And then we'll start to simplify left to right, so negative 7, that double negative turns to a positive, and then plus or minus the square root of, see, negative 7 squared, just positive 49. And then this is a negative 4 times negative 2, which is positive 8, and then times a positive 1, so this will be a plus 8. And then over 2 times negative 2, which is negative 4. And then from there we can add inside the radical, so negative, or just 7, sorry. And then plus or minus the square root of 49 plus 8, so 57 over negative 4. And then the square root of 57 can't be simplified, but I think your workbooks are starting to ask you to get decimal approximations for when they're wanting x-intercepts, but like there's not exact ones. So we'll go through how to get a decimal approximation for this. So from this point, since the radical can't be simplified, we need to separate it into two equations, one with plus and one with minus. So I'm going to do x equals 7 and then plus the square root of 57 over negative 4, and then I'm going to leave a gap and then put the other one over here. So x equals 7, and then this one should have a minus the square root of 57 over negative 4, because we just had to separate out the plus or minus. And then at this point, I'm going to get a decimal approximation for the square root of 57. So it's about 7.55. So we'll replace the square root of 57 with 7.55, so it'll be 7 plus 7.55 over negative 4, and then 7 minus 7.55 over negative 4, and then we'll just simplify each separately. I'm going to bump this one down here, just give myself a little bit more space. So if we do 7 plus 7.55, it's 14.55 divided by negative 4 is negative about 3.63. So negative 3.63. If you want, you can do like the little kind of curvy equal sign to show like approximately. And then the other one I'm going to do down here. So we'd have to do 7 minus 7.55, which is negative 0.55, and then divide that by negative 4, which is about 0.14, depending on how and when you rounded. So our x-intercepts for this function, like even though they're kind of ugly, even though they're approximations, we did find them. They are negative 3.63-ish and 0.14-ish. So 7.2 introduces vertex form, which is a new different form that we can write quadratics in. So the formula for vertex form is f of x equals a times x minus h squared plus k, where h and k is the vertex. That part is really important. One thing I want to point out that's going to come into play once we get into these problems is this x minus h means that whenever you're trying to figure out what h is, it kind of is the opposite of what it looks like it should be because of that minus sign. So we'll talk about that more in a second. So example 1, rewrite f of x equals x squared plus 4x minus 5 in vertex form and then state the vertex. So as it's given to us right now, this is the same function we've been working with this entire set of notes. It's in standard form. We want to put it in vertex form. In order to do that, we have to use the same process that we would use for completing the square. So I'm going to rewrite it down here. So f of x equals x squared and then plus 4x and then minus 5. So when we're completing the square, we usually isolate the terms that have x squared or just x in them. You can add 5 to cancel it out and put it over here, but we're going to end up having to isolate that f of x anyways. So instead of doing that, I'm just going to move this negative 5 over and just leave myself some space. So I'm going to complete the square with just this x squared plus 4x. Sometimes I like to put brackets around it and the space, just really emphasize that I'm only focusing on that part of the function right now. So when we're completing the square, we have to find b over 2 squared, which b is 4. So I would find 4 over 2 and then square it, and 4 over 2 is 2, and then 2 squared is 4. So I would add 4 right here to complete the square. Normally we would add 4 to the other side of the equation to keep it balanced. So you can do that, but knowing that we're going to isolate the f of x anyways, instead of adding 4 to that side, we can just go ahead and do a minus 4 over here. Because if I add 4 and subtract 4 from the same side of the equal sign, I'm not making any changes. I'm keeping the value the same. They kind of offset each other. So from there, I'm going to go ahead and factor. So it's f of x equals, and remember, whenever we complete the square, it factors into a pattern. So it factors into a binomial squared. So we would take the square root of the first term. So the square root of the first term is x. And then we take the sign from the middle term. So since that's a plus, we would do a plus. And then the square root of the third term, so the square root of 4 is 2. So x plus 2 squared. And then outside of the bracket slash parentheses, we would go ahead and combine these two. So negative 5 minus 4 is negative 9. And then now this is in vertex form. So it's a binomial squared, it has to have that. And then it's okay if there didn't end up being a number out there. There usually will if you change it from standard form. But the main thing that has to be true for it to be in vertex form is it needs to have this binomial squared. Okay, we don't have an a value, that just means that a is 1. And then now we want to identify the vertex. So the vertex is the point hk. So h is what's inside the parentheses with the x, and the k is what comes after. So the k is pretty easy to see, it's negative 9. But an easy mistake to make is saying that h would be positive 2, and it's not. It's technically negative 2. So that's what I was saying, where because of this negative right here, you actually have to switch the sign, because the h value that turns that x minus h into an x plus 2 would have to be a negative 2, because it's x minus negative 2. So basically when you're looking at an equation or a function and you're trying to figure out what h is, it's kind of the opposite of what it looks like it should be. So if it's x plus a number, h would be negative. If it was x minus a number, h would be positive. So vertex is negative 2, negative 9. And then now we can go ahead and answer all these little pieces on the right. So find the following features from the function in example 1. So first is max or min. So we know a few things about the function. So there is an a value, even though there's no number here. If there's no number, it's 1. But the bigger thing is that it's positive. So it's positive. So that means that the graph is opening upward. And we also know the vertex, so I'm just going to put that right here to give us a visual. We just found the vertex is -2, -9. So since the graph opens upward, there's a low point at the vertex, and that means that this graph has a minimum. So every quadratic has a minimum or a maximum, not both. It just depends on if the graph is opening up or opening down. And then the height itself of the minimum or the maximum is the y-coordinate. So like this graph has a minimum at the vertex, which has a height of -9. So our minimum is -9. And then for where it's increasing or decreasing, that's like when we follow the graph from left to right. So if we follow from left to right, it starts off going down, so decreasing on the left side. And then after it hits the vertex, it starts going up and it's increasing after that. So that boundary line is a vertical line that goes through the vertex. Since like it's a vertical line, that's the line x equals -2. It just goes through the x coordinate of the vertex. And that's our boundary line where it shifts from like decreasing to go to increasing. So I'm going to write this in interval notation. I'm also going to introduce a different way of writing like these, where it's increasing, where it's decreasing. So in order to write where it's increasing, so it starts increasing at x equals -2, and then it's anywhere to the right of x equals -2 is where it's increasing. So if it's starting at -2, it'd be between -2, and then the right side of it would be up to infinity. And then at -2 exactly, it's like neutral. It's not increasing or decreasing. So we would have to put a parentheses around -2 and then always a parentheses around infinity. Because you can't like have something include infinity. It's not like an actual number. Remember, between parentheses and brackets, a bracket would mean that it includes that number. And then an alternative way of writing like these intervals, which the workbooks kind of started to introduce, is with inequality symbols. So another way of writing it, I'm going to give myself a little bit more space. Another way of writing it is with an inequality symbol. So since it's saying it's increasing like between when x is between -2 and infinity, you would write when x is less than infinity or greater than -2. So it means the same exact thing, it's just a different way of writing it, and you need to kind of be exposed to those different forms. Okay, so when it's decreasing to the left side of -2, so basically like the left side of -2 means like starting at -infinity and going up to -2. So this would be between -infinity and -2, with like -2 being on the like higher end of it, since obviously -infinity goes down forever. And then parentheses around -infinity because we can't include it, parentheses around -2 because the -2 is neutral, it's not increasing or decreasing. And the way we would write it with an inequality is we would say x is less than -2 and greater than -infinity. I did not leave myself enough room, I'm sorry. So x is less than -2 and greater than -infinity. Let me just move this down so it's not as smushed. Okay, so try to get comfortable with both ways. You'll see both pop up in your workbook, so you just want to maybe leave a note or like have a little like note card if you could reflect back to them and kind of compare where they're the same and where they're different. Okay, so domain, technically for all quadratics, the domain is all real numbers, but there's a bunch of different ways to write that. It's basically domain is like how far is the graph going, like, or extending from left to right. And we've talked about this in I think lesson 5. But quadratics go left and right forever. Even though they look like they're starting to go like pretty vertical, they're always like inching outward towards the left and towards the right. So one way of writing like all real numbers for a domain that I don't think you'll see in your workbooks, but it's like a nice shorthand to know, is that capital R with the extra line through it means all real numbers. And then another way of writing it is an interval notation, and it's just from -infinity to +infinity. Or you can write it with the inequality. So domain is the possible x values. So it'd be x is less than infinity and greater than -infinity. And then range is all the possible y values. There is a low point, like a minimum, so the range can be all real numbers because -9, we already talked about, is like the lowest possible point on the graph. So in interval notation, if -9 is the minimum, that would be kind of like the starting point. So to go from -9 and then up from there, so up to infinity. And since we have a point at -2, -9, that's where the vertex is, we would put a bracket around -9 because it does include that, and then a parentheses around the infinity. And then for the like inequality notation, since range is the possible y values or output, you can either use f of x or y, but it would be like y is less than infinity and greater than or equal to, because it includes the -9, -9. Okay, so I know it's a bunch of different ways of writing the same thing, but I would maybe like try to screenshot this so you have it to like kind of reflect back on, because it can be kind of tricky when you're first practicing them. Okay, 7.3, we're going to start graphing. So graph f of x equals x squared minus 2x minus 8 by using some of its key features. So my goal is to find the y-intercept, the x-intercepts, and the vertex. So I'm going to start with y-intercept first, because that's the easiest. So for my y-intercept, remember that it is just my c value when it's in standard form. So in this case, c is -8. So our y-intercept is -8. I can just go ahead and put that on the graph right now. We have a y-intercept of -8, so there's a point there. For the x-intercepts, I want my graph to be in, or I want my function to be in factored form. So I'm going to go ahead and factor it. I'm going to set it up as f of x equals x squared minus 2x minus 8. And then a is 1, so that means I just need numbers that multiply to -8 and add up to -2. Whenever a is 1, that's the case, so multiply to -8, add up to -2, I can do -4 and +2. So this would be f of x equals x minus 4 times x plus 2. And then when we're finding the x-intercepts, we swap f of x out for 0. We find the zeros of the function. So I'm just going to go ahead and erase this just so I don't have to rewrite the same line. So this is going to become a 0 equals x minus 4 times x plus 2, because that's how we find the zeros / x-intercepts. And then now it's in factored form, so I just need to set each factor equal to 0. So I would do x minus 4 equals 0 and x plus 2 equals 0, and then solve each one separately. So I would add the 4 over to get x equals 4, and I would subtract the 2 over to get x equals -2. So those are my x-intercepts. So I can go ahead and graph those also. So I have an x-intercept at 4, so right here, and then I have an x-intercept at -2, so right here. And then now I need to find the vertex. So you can find the vertex a bunch of different ways. I'm going to find it by changing my function into vertex form. So I'll take my function up here, so f of x. I'm going to actually title this just so you guys can kind of reflect back to it. So f of x equals x squared minus 2x. And then remember, when we're changing from vertex form, or sorry, when we're changing from standard form to vertex form, we're going to complete the square. So I kind of want to leave this x squared minus 2x separate from like the -8. So I'm going to bump the -8 out. I don't need that right now. I'm going to close brackets around it so I can just kind of focus on the part that I'm completing the square with. And then I need to find b over 2 squared, which in this case b is -2, so it would be -2 over 2 squared, which is -1, and then I have to square -1, and that gives me a +1. So I'm going to add a 1 right here, and then I need to offset that in the equation. So I have two ways of doing that. I can either add the 1 on this side to keep it balanced, or I can just subtract 1 over here, because adding 1 and subtracting 1 is not making any change. It's keeping the same value. So f of x equals, and then I can go ahead and I can factor this. So it always factors into a binomial squared when we complete the square. So square root of the first term, so square root of x squared is x, and then I take the sign from the middle term, so since that's a minus, I'll do a minus, and then the square root of the third term, so the square root of 1 is 1. And then over here, I can go ahead and I can combine these, so negative 8 minus 1 is negative 9, and then now it's in vertex form, so f of x equals x minus 2 squared, minus 9, and then to find the vertex, I need to find my h and k. So h is 1, k is negative 9. So my vertex, remember, it's h is positive 1 because that minus is like embedded in the formula itself. If we look up here, that minus is already there. So that means that h is positive 1 and k is negative 9. So my vertex is 1, negative 9. I can put that on my graph here. And then that looks like enough to be able to sketch my graph. So it's going to go up from negative 9 up to negative 8 up to negative 2. And then we know that like quadratics are symmetric, so I should have another point exactly right here. And then I can go ahead and I can connect through. And then the last example says I examine the graph and write a rule that represents the quadratic function. So the rule can be in any of the three forms, standard form, factored form, or vertex form. It just kind of depends on what you're given in the problem. So we want to look at what like important points we're given. So if I look at like where my x-intercepts are, those are not exact points. I know it's kind of hard to see, but they're like offset a little bit. So if they're not exact points, we can't use factored form because that would be like where we have those x-intercepts and can plug those exactly in. But we do know the vertex. So that looks like exactly on the point to negative 4. So since we know the vertex, we should use vertex form to write our rule. So the vertex form formula is f of x equals a times x minus h squared plus k. So for when you're given the vertex, remember that the x-coordinate is h and the y-coordinate is k. We can just go ahead and take those both and substitute them into the formula itself. So we'll put 2 in for h and we'll put negative 4 in for k. So f of x equals a, and then x minus h is going to turn into x minus 2 because h is 2 squared, and then plus k is going to turn into minus 4 since k is negative 4. And then we're pretty close, but we need to find a to actually be able to like say that this rule perfectly describes this graph. So we don't know a, but we can take another point from the graph and use it to find it. We can plug that other point in for x and f of x slash like y, because remember f of x is just y. So it could be any other point, like exact point that we know on the graph. It looks like the only other point that we could tell looks pretty exact is like the y-intercept, so 0, 8, or like 4, 8 we could use. I'm going to go ahead and use the y-intercept, which is 0, 8, and it doesn't have to be a y-intercept. It could be any point that we like know is on the graph for sure. So I'm going to take those two, 0 and 8, and put them in for x and for y slash f of x. So we'll put 0 in for x, and then we'll put 8 in where f of x is. So it's going to be 8 equals, a is what we're solving for, so that stays as is, and then 0 goes in for x, and then minus 2 squared minus 4, and then now a is our only unknown, so we can solve for it. So we'll simplify the inside of the parentheses, so it'll be 8 equals a, and then 0 minus 2 is negative 2 squared minus 4. I need to simplify the right side of the equal sign with order of operations, so I would do negative 2 squared next. So 8 equals a times negative 2 squared is 4, but I'm just going to write it as 4a because we usually write like the coefficient, the number in front of the variable, and then minus 4. And then the right side of the equation is like as simplified as I can get it. So now I just need to start isolating my variable. So moving things away from it. So I can cancel out that minus 4. I'm going to add 4 to both sides to undo the subtracting 4. So 8 plus 4 is 12 equals 4 times a. And then to get rid of the 4 that's being multiplied by a, I can divide both sides by 4. And then 12 divided by 4 is 3. And then 4 divided by 4 cancels out. So I'm just left with 3 equals a. And then from there, I just need to take that 3 and I need to plug it back into the equation for a right there, the one that has like the h and the k plugged in. So it would be f of x equals a is 3, so it would be 3, and then parentheses x minus 2 squared, and then minus 4. So f of x equals 3 times x minus 2 squared minus 4.